Okie dokie artichoke. Hopefully at this point you have now determined the thickness, the height in those two calculation methods. One for density, that's the one we had up here on top in the last video, and one down here, the water displacement. Brain fart again. So you have those two methods, and hopefully you calculated your H value, and it was a small value. It should be in centimeters on the order of 10 to the negative 3, something like that, in terms of how many centimeters thick it is. That's pretty darn thin. What we're going to actually have to do, though, is take those centimeters and convert it to how many atoms thick. So we know that atoms are really, 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 really small. So how are we going to be able to determine how many atoms thick aluminum foil is? All right, this is, again, an indirect way of measuring those atoms, and we're going to come up with a way of doing that. So here's what you want to do. Now, once you have the thickness determined of your aluminum foil, okay, by those two indirect methods, you should do the following. So you have it now in centimeters. All right, it should be in centimeters. Now I did a calculation. I'm not going to do the calculation for you. I want you to do it, but I did do a calculation for one of them. Okay, all right, and it is on the order of magnitude of 10 to the minus 3. So I will tell you that. That means 0.00 something something. So you want to get that. So you're going to have some number here, whatever you calculated, times 10 to the negative third, or you might not. You might just have it as 0.00 something something, and you can leave it like that. That's fine. But you have measured that in centimeters. That calculation is in centimeters. You need to figure out how many picometers. Pikachu. Pikachu. Anyone? Pika? Okay, no, I'm not talking about Pika. Although he's a little cute little guy, yeah. Who does he evolve into? Pokemon's evolve, right? Raichu. Woohoo! Don't mess with Raichu, okay? He's the man. Oh yeah, okay, so we need to calculate this into picometers because on the sheet, we gave you a thickness of what an aluminum atom is. So if we know the thickness of an aluminum atom, and we know how thick the aluminum foil is, we should be able to calculate how many atoms thick the aluminum foil is. And the measurement was given on the handout in picometers. That's why we need to get this into picometers. How many picometers thick is this? So we need to get that so we can then determine how many atoms we have in our aluminum foil thickness. So you want to get this into picometers. Centimeters goes here on the bottom because you want it to cancel, right? This is some dimensional analysis review. And we want to go from centimeters, cover up, go to meters. And let's go ahead and put some numbers in now. Who's bigger? Meter. How many centimeters? 100. Okay, that will give us the thickness in meters, and then let's go to picometers. All right, now, meters is on the top, so it goes on the bottom. Now I have no prefix here, so I can put whatever I want. I'll put pico. Who's bigger? This is the question you have to ask. This is a lot of times students will make this mistake. If I'm not guiding you through this, you make this mistake, and I have to go through it several times with a lot of students. So let's just get this right now. Who's bigger? Now, pico is not one of the basic international unit prefixes that I'd gone over earlier. Maybe I should have, because we use it this one time. Other than this, we don't use it anymore. Pico means 1 times 10 to the negative 12th. It's just beyond nano. Nano is 1 times 10 to the negative 9th, and there's pico, 1 times 10 to the negative 12th. That means it's really small. So it's really, really, really small. So who's bigger? The meters. The meter gets the 1. Okay? Picometers. It means 1 times 10 to the negative 12, but don't put that up there because that's not what they're not the same thing. So you're going to need a lot of these to equal one of those. You're going to need 1 times 10 to the 12th of these to equal one of those. So up here I have to put 1 times 10 to the 12th, or I can just put 10 to the 12th. It means the same thing as 1 times 10 to the 12th picometers. So that's my setup to get this into picometers. So when you do this calculation, you will get a big number. It's going to be a big number because picometers are really small, so you're going to end up getting a big number of how many picometers thick. Even though the aluminum foil is super, super thin, it's still many picometers thick. So you'll get a big number. So don't panic if you get that big number. All right, it's usually on the order of magnitude of 10 to the 7th. So if you get a number on your calculator, it might say times 10 to the 7th, or it might say this big number and you count backwards, it will be 7 places that the decimal place has been moved. So that if you get that, then you know you're on the right track. Now 10 to the 7th is in the tens of millions of picometers. So we will have a very large amount of these very small picometers, even in thin aluminum foil. Okay, so the last step then, well, actually it's not the last step, there's one more, we have to get a percent error, but the last step to determine how thick our aluminum foil is in atoms. Atoms, remember? Seeing if you're with me, tricked you, didn't I? Atoms. How many atoms of aluminum thick is our aluminum foil? How many atoms are there stacked up to make our thickness of aluminum foil? How many atoms? Okay, well on here, I wrote down that an atom is 118 picometers thick. It's called the atomic radius, 118 picometers thick. So, if you get this big number, picometers, big number, times 10 to the 7th, some blah, 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 times 10 to the 7th, then you know how many picometers thick it is, and it's 118 picometers per atom. So, I'm going to move this down here because I'm running out of room. I'm trying to think of picometers. Now, you want to get this into atoms. So picometers goes on the bottom, atoms goes on the top. 1 atom of aluminum, 118 picometers thick. So you're going to take this and divide it by 118. And that's going to give you how many atoms thick your aluminum foil is. So that should, hopefully you'll come out with a number in the order of magnitude. If this is 10 to the 7th and this is 10 to the 2nd, of 10 to the 5th atoms. So it'll be some times 10 to the 5th. Or it might, your calculator just might write it out as one whole number, which means it'll be in the hundreds of thousands. So you should have an answer for your number of atoms thick the aluminum foil is in the hundreds of thousands of, and it's usually in the lower amount of hundreds of thousands. So sometimes some students will get like 90,000 or something like that, but usually it'll be between 1 and 200,000 on average, maybe a little more or a little less. So you should be getting in the lower hundreds of thousands of atoms thick for the aluminum foil. Okay, then the last thing we're going to do is do a percent error. Now, if you look on the second page of the handout, all right, here are your questions. So you've done these calculations out, so make sure that you make a data table. Make some data table, set it up, do it however works for you, record the data that we recorded as lab partners together, then show your calculations. Now you're going to have 2 sets of calculations, remember, because we have 2 methods. So you have to go through these calculations 2 times. So you're going to do this once for the density, and then you're going to do it again for the water displacement. So you'll have 2 sets of calculations. You'll have 2 answers for how thick the aluminum foil is for the density and then for the water displacement methods. You'll have 2 of these calculations, 2 sets. Show them, write them out. Last, write out your percent error calculations for those 2 sets of data that you will now have for the 2 methods of getting the thickness. Okay, now what we're going to use, if we're going to do a percent error, we have to have a true value. So the true value is given in calculation number 1. Okay, there it is. True value to be used for the thickness of the aluminum foil, 1.93 times 10 to the 5th. Now the thing is though, that's kind of like a true value. The reality is with aluminum foil, there are different thicknesses of aluminum foil. I was using Reynolds wrap. Okay, you could go to the store and buy a Hannaford brand and it's going to be thinner. It is, it's going to be thinner. Or there's heavy duty Reynolds wrap, which is usually used for grilling and stuff. Oh, grilling. Oh, I'm grilling tonight. You know what I'm doing? I'm grilling some steak. That's right. I said it. Okay, where was I? I'm getting hungry now. Oh yeah, so aluminum foil itself has different thicknesses. So this 1.93 times 10 to the 5th is kind of like this average of all the aluminum foils. So it's not exactly a true value, but we're just going to use it to do the calculation anyways. Okay, so there's another potential error. The true value of the aluminum foil, this aluminum foil might not be 1.93 times 10 to the 5th. It just might not be, so that's what we're using. So go ahead and do that calculation. And the true value is 1.93 times 10 to the 5th minus whatever you get for your calculation for how thick the aluminum foil is. Put that here. And then divide by 1.93 times 10 to the 5th. You're going to take an absolute value. And this, remember, to get a percent, always multiply by 100. An absolute value means ignore any negative. Multiply by 100. And that'll give you your percent error. You know what? Your percent errors might be high. Who knows? It might be low. Which method is better? I don't know. Let's find out. Let's just find out. Was this aluminum really just all aluminum, or were there something else mixed in with it? It's one potential error. The other thing is, did I really get all the air out of it? Probably not, meaning that volume was probably a little bit bigger than it should have been. But it's, that method is best we can do. And I squeeze people. You should have seen me. I have a broken thumb right now. I have to go get this thing casted because it's so sore. I broke it trying to squeeze the air out. Okay, I'm here for you. Okay, you people just sit back, relax, and enjoy the show. I'm out here on the front line. Okay, front line. I'm here for you. All right, so do those percent error calculations. Show 2 of them, because you will have 2, one for both methods. And then go ahead. Now, that's a calculation for that first question. So if you have any questions on these calculations, you're doing them, going ahead and going through the process, and you get 8,000% error, that's bad, that's wrong, you've done something wrong. Or if you get, I was going to say 1% error. Hey, maybe we will get 1% error. Who knows? Probably. You might have done something wrong. But, usually we try to shoot for, this is a rough one because we have different kinds of foil, different amounts of water displacement because of the air problem. I would say 30%. If we can get 30% or less, and I have not done the calculations out. I haven't. I really have not on it. Boy Scouts honor. I don't remember. I was a Boy Scout for like 8 months and they kicked me out, basically. That's a long story. So I have not done the calculations out. All I have done is I did one calculation for the thickness to see what I got. I'm not going to tell you. I'm not going to tell you what I got. But you go ahead and do it, see what you get, and hopefully we get within 30%. Okay, that's pretty good for a lab like this, which has a lot of assumptions and ambiguities in it. All right, I think that's it for the lab. I think that wraps up what we need to do for the calculations. Of course, you have a week to do this, so if during the course of that week you have any issues, problems, let me know, and we'll see. And I'm actually going to go back and do the calculations myself and see what I get. All right, okay, bye.